Along this afternoon. Great pleasure to see so many people here, and a pleasure to introduce Todd Hufnangel. Todd grew up in Michigan, I think, is that right?
In Michigan, yes.
And developed an interest in extreme conditions on the Great Lakes, fishing for fish through ice.
Through the ice, yes.
He went to
Michigan Tech.
And that's where he did his bachelor's. And then in the closing decade of the last millennium, he migrated to Stanford and did his master's and PhD, and that's where we met.
Where the conditions were less extreme.
Yes. We both at that time had a shared interest in metallic glasses and have worked together on that area. In 1996, Todd moved to Johns Hopkins, where he's been ever since, professor of material science and engineering. And reading from what his employer says about him.
I think I probably wrote it.
He's Associate Director of the Material Science and Extreme Environments University Research Alliance. And this is a group of 18 major research institutions focused on mitigating the threats posed by chemical, biological, and nuclear weapons. All sounds quite extreme. Anyway, it's quite a pleasure to hand over to Todd to hear about this exciting development.
Great. Thank you, Lindsay. Thank you for the kind introduction. It's great to be back in Cambridge. I will say that the reason that I'm in the UK right now is because my son is a fresher at what is known as the other place. Is that what we refer to? Yeah. So we were over there visiting him. But I was, as we were in Oxford, I was remembered of talking with Lindsay at, I think, an RQM meeting in Oxford about 2002, 2003 or so. And I have an interest in naval history. And I wanted to go down and visit HMS Victory down in Portsmouth, but I didn't know how to navigate the trains. So at lunch, I went to Lindsay and I said, Lindsay, I have a question that only an Englishman can answer. How do I get on the train to go to Portsmouth? And Lindsay gave me his wry smile and said, well, actually, I'm an Irishman, but he was kind enough to give me the directions anyhow. So thank you for the invitation. So I'm here today to talk about this laboratory that we're building at Johns Hopkins. We call it the Artificial Intelligence for Materials Design Laboratory. And it's intended to be, at first, an automated high-throughput laboratory, and then ultimately become an autonomous laboratory for doing materials research in structural materials in particular, and for materials in extreme environments even more particular. So to frame this, I want to show you this picture. This is the laboratory of Thomas Edison, who is famous, of course, for perfecting the incandescent light. This laboratory was at his lab in, this room was at his lab in Menlo Park, New Jersey. It has since been purchased, or many years ago was purchased by Henry Ford and moved to a place called Greenfield Village outside Detroit in Dearborn, Michigan. If you find yourself in that part of the world, I highly recommend a visit there because it's sort of a remarkable place. But they basically recreated Edison's lab. And you can see all sorts of fun stuff, including a pipe organ there in the background. But the reason I show this is because Edison's chief challenge in creating the incandescent light was finding a material that could be used as a filament in that light. And so over the course of about 2 to 3 years, they tested approximately 3,000 different materials, looking for either a synthetic or naturally occurring material that could satisfy the need to glow brightly, but also last in an incandescent light. And if you do the math, that's about 5 materials per day for this research team doing that kind of experiment. It's not exactly what we would call high-throughput science. So today in the 21st century, we have things like this. So this is the A-Lab, which is at Lawrence Berkeley Laboratory out in California. So the A-Lab is an artificially intelligent guided materials synthesis process where the artificial intelligence machine learning algorithms are making predictions about the processing conditions that are necessary to produce a particular compound. And so this robot is taking powders, it's weighing out proportions of powders, it's mixing those powders together, it's putting them in a sintering furnace, as you'll see here in a second, to try to produce a chemical reaction to produce a particular crystallographic phase that the AI algorithms have predicted can be made. So this, a lot of people think, is the future of materials research, or one future of materials research. And there have been lots of papers written, and this is just a selection of review articles from just the last 3 or 4 years on this idea of high-throughput, automated, autonomous research. It's clear that lots of things can be done. It's clear that we can move very quickly, that we can examine a far greater range of materials and a far greater set of conditions than is possible if the humans are doing the experiments all the time. But there's some challenges. And today what I want to talk about is our lab and how we address some of these challenges. Not all of these are specific structural materials, but our particular interest is in structural materials in extreme conditions. So the first, and this is a common challenge, the parameter space can be very large, right? It's easy to talk about, if I want to make an alloy, a binary alloy or ternary alloy, how many different possible combinations of those elements there can be in all different concentrations. But in structural materials, and you can also think about the processing parameter space in terms of just simple heat treatments, right? Anneal at a particular time for a particular temperature, do a particular cooling schedule, do some sort of thermomechanical processing to introduce some particular dislocation structure in the material. So the processing parameter space is huge. Generally speaking, AI and ML algorithms are data hungry, so that goes along with this idea that the parameter space can be very large, and that means we need lots of data. We need to either be able to do lots of simulations and do lots of modeling, or we need to be able to do lots of experiments. In the case of structural materials, we're often dealing with multiple objectives, right? We're not simply trying to make a material, we're trying to make a material that has a particular set of properties. So the classic trade-off, of course, is strength and ductility. It's easy to make a strong material. It's hard to make a material that is both strong and ductile. And those objectives can often be in conflict with each other. We're going to talk about a variety of different tests. Those different tests provide different information. And so we need to figure out how to combine those different sources of information. And those tests have different costs. It may be possible to do one test which is relatively fast and inexpensive, but provides you with sort of low fidelity information, versus another test which may be much slower and much more expensive to do, but provides you with a richer set of information. How do you judge which experiment you want to do when? And then the last one, and I'll spend a minute talking about this, is that for mechanical behavior in particular, microstructure matters. So in the case of the A lab, for example, they're just trying to produce a particular crystalline phase. They don't particularly care what the grain size of that material is or what its microstructure is. They just care that they made the phase. But of course, for mechanical behavior, microstructure is everything. And so we have to worry about that as well. What goes along with that is in the case of mechanical properties, length scales also really matter. So in a lot of the autonomous labs, many of them are simply focused on processing and making things. But even the ones that are looking at properties, many of them are looking at functional properties, which are not so sensitive to the microstructure of the material. When I start looking at behaviors like ductility, for example, the microstructure is critical, and the conditions under which I do the test, the size of the sample, the strain rate, these sorts of things are all really important. So length scale matters. So we all know, of course, atomic length scales, what crystal structure do you have? Is your material FCC or BCC? The defects that you have, dislocations, what does that structure look like? The structure on the micron scale, the microstructure, what's the grain size distribution, what's the crystallographic texture, all those things matter. And then for mechanical properties, even things at the continuum scale matter as well. And the key is that you have to be able to fabricate, characterize, and test your materials on the scales that are length scales that are relevant to the problem that you have in mind. And if you can't do that, then you're not going to learn anything that's useful. So here's our answer to this. This is a photo of the inside of this AIMDL laboratory. I'm going to describe the laboratory in broad terms and then just drill down in a couple of particular areas where this lab is sort of unique. I'm actually not going to spend very much time talking about the science and the data that we've collected. I'll give you a few examples, but I'm going to focus on the lab itself because honestly, the lab is its own research project. So here's a plan view of the lab. If I go back actually one slide, you notice sort of at the heart is this conveyor system, which is moving our samples around. Oops. Oh, now I've confused it. Oh, there we go. Okay, here we go. So here's a plan view of the lab now. So here's that conveyor system, the sort of staple-shaped thing. And as we go around that conveyor system, you can see a variety of experimental stations. There's one for doing profilometry, looking at surface stress and surface topography of samples. Also nanoindentation for looking at quasi-static mechanical behavior. I'm not going to talk about either of those because those are basically commercial instruments that we bought off the shelf, and our role has basically been just to integrate them into our automated workflow. What I will spend some time talking about are our microstructural characterization, because we have a unique instrument for that, and then also how we measure dynamic mechanical behavior of our materials. So I'm going to start with that. We have a unique system that we call laser microflyer impact. I'll begin with that. Then I'll talk about microstructure with another unique system for doing high energy X-ray diffraction in the laboratory. And then I'll finish the talk with a discussion of data. Because it turns out that if you think about a lab like this as a collection of individual instruments, and you don't put a lot of thought into the data and how the data is going to move around and how it's going to be used, then all you have is a collection of individual instruments and not a lab. So the data part is really the glue that sort of holds this lab together. Okay, so let's first begin by talking about dynamic mechanical behavior of materials. And I want to use one specific example. This photo is an illustration of what's called spall failure. This is a photo actually from the European Space Agency. And what the photo shows is a slab of aluminum. I forget exactly how many centimeters thick, but this is an aluminum ball. That one is 1.2 centimeters in diameter. Not this ball, but a different ball was launched at about 7 kilometers per second into this aluminum slab. And you can see, of course, this giant crater that forms, sort of like you would expect. But there's also this failure feature down here. Right? That is indicative of what we call spall. And it's associated with a tensile failure mode in this material, even though, of course, the impact of the sphere on the surface creates a compressive shock wave. And I'll describe for a second how that happens. One thing that I do want to point out, and to show you why length scale, or how one way in which length scale matters, is if you notice the diameter of this sphere, as I said, is about 1.2 centimeters. That's just about this distance right there. And that's not an accident. And I'll show you why it's not an accident in a second. Okay, so let's just do a quick walkthrough of how spall failure works in materials. So what I've got at the left is just a diagram showing a schematic of some target material. If it's an experiment, then this is going to be my sample. So it's going to be a plate of material. And I'm going to send toward that plate a flyer. Could be the same material, could be a different material. And I'm going to launch that flyer at a velocity of, let's say, 1 kilometer per second. Right? So the flyer now has impacted the target. And now what we want to do is track how the different waves in the target and the flyer evolve over time. So we're going to create a diagram that looks like this. On the vertical axis is position, and this maps directly onto position on the diagram at the left. Horizontal axis is time as waves propagate. And we're going to keep track of 3 important surfaces. So there's the impact plane between the flyer and the target. That's where our shock wave is going to initiate. Then we're going to have the back surface of the target, which is a free surface. And then we also have the back surface of the flyer, which is also a free surface. So the first thing that happens is the impact of the flyer on the target causes a shock wave to propagate from that impact plane down toward the bottom of the sample. And then in time, we watch it go like this. Of course, the slope of that line is related to the speed of that wave. When that compressive wave gets to that free surface, it reflects off the free surface because, of course, there's a difference in impedance between the solid material and the air that's behind it. And when it reflects, it actually reflects back as a tensile wave. So now I have a tensile wave, which is propagating back in toward the interior of my target. Now, of course, exactly the same thing is happening in the flyer. So now there's a compressive wave in the flyer, which reflects off of the free surface at the back of the flyer as a tensile wave. That tensile wave is going to propagate into my target, and it's ultimately going to overlap with the tensile wave that's reflecting off the back surface of the target. And where those 2 tensile waves meet, I can have extremely large hydrostatic tensile stresses. And what those tensile stresses can do to the material is that it can cause cavitation, so nucleation of voids, which then grow. And if those voids link up, they cause the kind of spall failure that you saw in the previous slide. I'll just point out that in this particular diagram, notice that this dimension, the thickness of the flyer, is exactly equal to the dimension, the distance from the spall plane, the region where the hydrostatic stress is a maximum from that free surface. Right? That's the case if these 2 materials if the flyer and the target are made of the same material. And that's why the thickness of that region near the bottom of that spall specimen is just about the same size as the diameter of the sphere. A little bit more complicated problem. Now, if you want to study this, up until 5 years ago or so, you would use a piece of equipment like this. So this is an instrument that we call high-fire. This is a 2-stage light gas gun used to launch projectiles at velocities of up to 7 kilometers per second. This is in the Hopkins Extreme Materials Institute back at Johns Hopkins. As you can see, just based on the scale of this, you can imagine that these experiments are difficult and time-consuming to set up. If we do 2 tests per day, 1 in the morning, 1 in the afternoon, we're doing pretty well. And because given the cost of the consumables and the time and everything that goes in, each test costs us about $3,000. So if you're trying to train an ML or an AI model for some sort of Gaussian process regression or something like that, where you need many, many data points, this kind of experiment is both too slow and too expensive to be practical. So in the context of an autonomous lab or an automated lab, we'd like to scale this down and be able to do tests at a vastly higher rate. So this is what we do. So we have now this, what we call a laser microflyer shock facility. That entire gun facility that you've seen, in a manner of speaking, has been shrunk so it fits on a single tabletop of an optical table. It has two key components. It has a drive laser, which is going to drive a flyer, like in the schematic that I showed a second ago. And it has a measurement laser, which is going to measure the velocity of the back surface of the target. And neglected to mention this in the previous slide, it's looking at that back surface and how it's moving in response to the waves that reach it, which is our primary diagnostic in this kind of test. The other thing I'll say about this, and I'm not going to talk about this more, is that we have a heating laser now, so we can do measurements not just at room temperature, but at temperatures up to 900 degrees Celsius, which actually these days is only limited by our pyrometer and not by our heating laser. Okay, so let me show you how this experiment works. So our flyer now is going to be a piece of an aluminum foil. So here's a plan view of ordinary piece of aluminum foil. Here's the side view. Maybe it's 50 microns thick, approximately. I'm going to take that piece of aluminum foil and a glass plate, and I'm going to glue them together with some epoxy. And then I'm going to stack that on top of, before I stack it, I'm going to take a laser, I'm going to mill out a bunch of discs in that aluminum foil. And these discs now are going to be our little flyers. And so we've gone from something which is maybe a centimeter or more in diameter to something which is a millimeter or two in diameter and much thinner. So here's the side view of our laser milled disc. I'm going to stack that assembly on top of a Kapton spacer, a couple hundred microns high, and I'm going to put that on top of my specimen. And the way in which I'm going to do the experiment now is I'm going to come in with a drive laser. That drive laser is going to cause vaporization of the epoxy. The expansion of that vapor now is going to detach the aluminum foil disc and is going to launch it toward my target, again at a velocity of 1 to 2 kilometers per second. Once that little microflyer hits the target, now my waves propagate in the way that I just showed. And again, our diagnostic is to look at the back surface velocity with a technique that we call photon Doppler velocimetry and just watch again how that back surface responds to the waves that reach it. Here's what it looks like. This is a high-speed video of one of these laser microflyers flying just into free space, not into a target. You can see, it's nice, pretty flat. They don't always come out this flat, but it's pretty flat. One thing which we worry about a lot is, how planar is that impact of that microflyer on the specimen, and we have ways to monitor that as well. But that's what it looks like. Now, in the context of a high-throughput automated experiment, we want to be able to do these not simply as one-off. We want to be able to do a lot of them. So here's a photo of just one of these aluminum foils with all the discs that have been milled out. What we want to do is we want to be able to do every one of these dots corresponds to a test that we can do. We want to do it in an optimized, automated sort of way. And so with some clever graduate students came up with a process that they call see, move, shoot, where they use just an off-the-shelf algorithm to locate where these circles are, to draw a box around them, to drive the stage, to put that stage and that dot directly below the laser. And now every flash you see here is another test. So we've gone from being able to do 1 or 2 tests per day to doing a test every few seconds. So we increased the throughput of this experiment by several orders of magnitude, many orders of magnitude. If you look really carefully, you see a dot appear right there on the actual experimental apparatus. So miniaturizing this experiment allows us to automate and dramatically increase its throughput. Okay, let me give you just one example of some of the data that we can collect and the kind of experiments that we can do. So this is from a paper by Justin Wilkerson from a few years ago where they were looking at the Spall strength of copper in different forms, single crystal, polycrystal, and nanocrystalline. Spall strength is a function of the expansion rate. This is the expansion rate of the voids. You can think of it as being related to the strain rate. The data that are here, these experimental data points, are a significant fraction of all the experimental data that existed for polycrystalline copper at the time that this paper was written. The point I want to make here is that the experimental conditions matter. So the shock stress matters, the strain rate matters. In our experiment, those two things are linked. But the other thing that matters, of course, is the microstructure of the material, and not just the average microstructure, but the grain size distribution and how that grain size distribution varies from place to place. Because the scale of our experiment now has been shrunk so much. Now we're looking at a region which is maybe a millimeter in diameter through a couple hundred microns thick. Now you're starting to sense some of the statistics of the microstructural variation as you go from place to place on this foil. Things like texture also vary and are also important. So here's a set of 88 tests that were done. This is all on nanocrystalline top copper plotting out the relationship between spall strength and strain rate. I'll just point out, we did 125 tests, and by we, I should really say the group of Katie Ramesh, whose brainchild this whole thing is, did 125 tests in about 6 months. They did 88 in about 2 months. All the prior data in the literature was about 50 tests over 75 years. And for us, this is not actually an especially high rate. A graduate student doing this test, just working in a lab in a manual way, can now do about 100 of these tests per day. And we are thinking that when our test is fully automated in our laboratory, we'll be doing easily 100 tests per hour, probably more than that. And the rate limiting step there is ultimately that little stack of stuff that I showed you had to happen. The robots will be assembling that, right? And there's just a limit to how fast the robots can actually do that. And that's going to ultimately limit our throughput on this experiment. Okay, let's move now to microstructural characterization. So the kinds of things we'd like to be able to measure to look at the microstructure, all the kinds of things you might expect. So what phases are present and how much? What's the grain size, average grain size, the grain size distribution, and what's the crystallographic texture, and so on. But the key here is we're not trying necessarily to get really precise, high-fidelity information about single points in the material. We want to rapidly be able to look at large quantities or many different places on a material in order to identify differences in structure. So one example would be, if this is my sample, and this is, let's say, some sort of combinatorial sample, or maybe I've produced such that there's a gradient in composition across the sample, or maybe a gradient in plastic strain and therefore microstructure. I'd like to look at a bunch of different points and not worry so much about the details of the microstructure at any one point, but just to be able to say, well, is this point different from the previous points that I've already looked at? Because that makes that point interesting. So if you want to do this, the easiest and the most obvious choice is EBSD, right? Which has been sort of the tool of choice in physical metallurgy for 20 years or so. You can do it reasonably fast. These days, you can acquire EBSD patterns at a rate of about 1,000 per second or so. You get pretty good spatial resolution. You, of course, can directly measure the grain size distribution and the crystallographic texture. And then as a bonus, because you've already put it in a microscope, you can do chemical composition by EDS. So this is really obvious. And a good friend, Dan Miracle, made this statement in his review article on high-throughput characterization of structural metals back about 4 or 5 years ago. Naturally, we decided not to do it that way. And the reason is that EBSD has some important limitations. And maybe the most important limitation is in the context of a high-throughput autonomous lab, where you're potentially looking at many different kinds of materials. Preparation of the sample becomes a huge challenge. If you've done EBSD, you know that your success or failure often depends on how good a job you can do of preparing that surface. The idea that we could use something like a RoboMet to do surface preparation, yeah, we could do that. Thus, the RoboMet itself was going to be about half of our budget for structural characterization. But the real interesting part of that problem is, if I have an unknown material, how do I develop the recipe that I need in order to let the RoboMet do its job? And so that seemed like a research project in its own right. Another limitation of EBSD is that it doesn't examine the bulk microstructure, right? It only examines the surface. But if you're doing mechanical properties on samples which are a few hundred microns thick, gradients in that microstructure through the sample might be really important. And EBSD is not going to be able to tell you about those if you're only looking at it in plan view. Another problem was pattern indexing. So if you have unknown crystalline phases, EBSD pattern indexing is pretty straightforward if you know what phases are present. But if you don't know, and particularly if you have unknown phases, then that's a major, major challenge and is a research project in its own right. So what do we decide to do instead? We turn to X-ray diffraction, because I'm an X-ray guy from a long time ago. In particular, we're going to do high energy diffraction, which allows us to operate in transmission. The big advantage there, the two biggest advantages, is that we get a true bulk through thickness measurement. We're equally sensitive to the front of the surface, the front of the sample, and the back of the sample, and everything in between. We can scan large areas really rapidly for reasons that I'll show you in a second. But maybe the most important reason is that it places minimal demands on sample handling and on sample preparation. If the sample surface is a little rough, no big deal. We're going to shoot right through it anyhow, and it doesn't matter. Also, things like phase identification, quantitative analysis are basically solved problems in X-rays, and so that's fine. And we can still get some crystallographic texture information if we're doing two-dimensional X-ray diffraction, as I'll show. So really, I guess one of the points here is that, again, you have to balance your desire for throughput and your need for fidelity of the measurement. And really, the right way to think of this is not EBSD versus X-ray diffraction. It's that X-ray diffraction can provide a very low fidelity but very rapid test at very low cost, whereas EBSD, particularly if you're doing high resolution EBSD, is a much slower technique, therefore it costs a lot more expensive in terms of time, but provides you with a much richer set of information. So really the way to look at this is to say, all right, we're going to use X-ray diffraction, we're going to scan across relatively large areas, and then we're going to go in and we're going to identify the regions that are particularly interesting, and then look at those with our high fidelity techniques. So here's an instrument that we designed to do this. It's X-ray diffraction experiments. The basic concept is here in the middle. So here's our sample. It could be several centimeters in extent. It's a foil, maybe a few hundred microns thick. Our X-rays now are focused to about a 200 micron spot. They're high enough energy that we can go through that sample and record an X-ray diffraction pattern in transmission. So here's an example here. This happens to be just a 7000 series aluminum alloy. This particular sample was about 1 millimeter thick. But because of the high intensity of our spot and the sensitivity of our detector, this diffraction pattern was recorded in about 10 seconds. So if we want to do like a 10 by 10 grid on a relatively large sample, we can easily do that in a matter of minutes. All right, so it really is a high throughput technique. As I mentioned, the distribution of intensity around these rings tells you something about the crystallographic texture. If you want to do phase identification, of course, it's easier to then integrate around those rings to get a one-dimensional diffraction pattern, and now you can do your standard phase identification sorts of routines. As long as we have an X-ray beam shining in the sample, we're going to get fluorescent X-rays out, so we might as well stick an X-ray fluorescence detector there and allow us to measure composition, which is helpful if we have one of these compositionally graded samples. The big limitation here, and I'll show this later, is that because this is all done now in air, we're not very sensitive to very light elements, and I'll show you an example of that before. But for transition metals and things, it works great. Give you an idea of the kinds of things that we can look at. This is a plot of the absorption length for X-rays as a function of the atomic number. So 8 keV is sort of your standard garden variety laboratory diffractometer that uses the copper K alpha wavelength. The anode that we use uses the indium K alpha. That's at about 24 keV. One absorption length turns out to be the optimum thickness for a transmission X-ray diffraction experiment in terms of signal that you get out. So you can see for aluminum, all right, one absorption length is about 2 or 3 millimeters. So we can look through a pretty thick slab of aluminum. Same thing with titanium. Iron is down here. It's about 100 microns or so. Doesn't mean we can't look at thinner things. It just means that, or thicker things. It just means that it takes a little bit longer. Where we do run into trouble is if we're now starting to look at things that are like in the second row transition metals, right? So things like niobium, these absorption lengths now are pretty short, on the order of a few tens of microns. So we have done niobium. We can look through, 100 microns or so. It just takes longer, right? We have to count longer. So we don't get our 10-second count times on that material. So here's the instrument that we designed and built with the help of a company formerly in Michigan, now in Canada, called Proto Manufacturing. The heart of it really is the X-ray source. So this is now a source, it's called a metal jet source. It's the anode now is a liquid indium tin gallium alloy. And we use it because outside of a synchrotron, for the spot size that we need, it's pretty much the brightest source you can have, again, outside of a synchrotron. And the reason that the brightness is important and not simply the power is we take that very small X-ray source size and we reflect those X-rays off of a pair of elliptically graded multi-layer mirrors. And it's those multi-layer mirrors now which are providing the focusing onto the small spot on the specimen. And so now our spatial resolution is basically 200 microns on the sample. This is the other reason for going to a transmission geometry instead of reflection, where now in reflection, your beam, of course, is spreading out over some area on the sample, and we wanted to avoid that. We have a nice, very fast, very low noise detector, and it's all automated, as I'll show you here in a second. So there's a picture of the instrument itself. Here's the business end of things, X-ray source. X-rays are coming out here. This robot arm is holding a sample in a sample holder. Nice thing about the robot, of course, is that we can hold the sample however we want. We have lots of flexibility in that. Here's our fluorescence detector. Here's our diffraction detector. All right, so just to give you an idea of how the lab overall works and how the automation works. So now you can see one of these samples in a holder on the conveyance. The robot has just picked it up off. For reasons associated with how the lab automation works, we always don't go directly into the instrument. We put it on a buffer, and then we move it into the instrument. So now the robot is going to hand the sample off to another robot, which is on the inside. Now the graduate student is going to quickly run around to the other side of the instrument with his phone. There we go. to show us what's happening on the inside. You can see the inside robot has grabbed that sample and has held it in front of the X-ray beam, and in a second here, the X-rays are going to come on, and the exposure is going to start. And now we can raster that sample and do measurements at different points on a flat specimen, and then we can unload and do all the kinds of other things you might expect. So just to give you an idea what the data look like, this is pretty recent stuff. This is from the group of Tim Weiss at Johns Hopkins. So they are making these combinatorial foils. They're interested in copper titanium. So we have a sample which looks like this. The dimensions here is this is like 20 centimeters or so going from top to bottom, and maybe 10 centimeters going across. It's compositionally graded, so it's rich in titanium at the top and then poor in titanium down at the bottom. We want to know both what the composition is and also what the microstructure looks like. So looking first at the X-ray fluorescence, here's the copper K alpha and copper K beta. There's actually several different samples on this plot, not just the two that I showed. You can see the copper quite clearly. You can see its intensity is changing as the composition is changing, but you can see that we have real difficulty in seeing the titanium. And again, that's because we're trying to do this in air. Diffraction looks like this. So now we have our diffraction rings like you expect. If I take these and azimuthally integrate them, I get a one-dimensional pattern that looks like this, just like you expect. Looks like FCC solid solution. If you look really carefully at the higher angle peaks, you can see a little bit of shift, which is associated with the change in lattice parameter due to the incorporation of titanium into this solid solution. So these are the kinds of things that we can do, but again, we can do it really fast, and we can do many, many of these measurements really very quickly. Okay, last thing I wanted to talk about was data, right? So I mentioned that at the very beginning, the data and thinking about data is really important when setting up a lab like this. And speaking as an experimentalist from these many years, time gone by, I think of data as something I collect, right? I run an experiment, I have a data, it exists as a file, I save it on my computer, maybe I upload it to Dropbox or whatever if I want to share it with somebody. But in the context of an automated or autonomous lab, you really need to think about data and data production as an event. And the data production is an event that can then produce automated responses. So those automated responses can include things like curating the data, right? Data, putting it in some data portal where other users can access it, reducing the data or extracting information from the data or doing some sort of analysis that can happen in an automated way as well. And then ultimately what you want to do is you want to enable some sort of decision making. Now the key, of course, is that the responses that happen to the production of data are themselves events, and they can elicit other responses. All right, so you have this sort of virtuous cycle of things that are happening in response to each other. So that's illustrated kind of in this Venn diagram. It's incorrect, I think, to think of it as data production followed by analysis, followed by curation and sharing, which is the way sort of traditionally we would have done it. Instead, all of these things are happening in interactive ways, essentially simultaneously. And what I want to spend the rest of the talk talking about and showing you is how we do this in this lab. I'm going to introduce this idea of what we call stream processing with something that everybody I think is familiar with, which is getting a ride on Uber, right? So if you want to ride on Uber, you pull out your phone. On your phone, you have the Uber app, right? You call up the Uber app and you say, I want a ride. Right? So you are now becoming a producer of data, right? And the data that's relevant to that request is where you are, well, who you are, where you want to go, and what kind of car you want. So you've created that really, really small amount of data, and that creation of that data then becomes what we call a ride request event. And your app sends that ride request event up to the Uber servers up someplace in the cloud. So you're producing data. On the other hand, there are other people that want to consume the data that you're producing, and those people in particular are all the Uber drivers. So the Uber drivers are all listening for these ride requests events. Actually, I should say the app on the Uber driver's phone is listening for these ride request events. And when they see a ride that they want to give, then they will create their own event, with its own data, which we call a ride accepted event. And that now goes up to the Uber cloud. And that has in it information about who the driver is, what kind of car, license plate, and so on. Now, some part of this process, there has to be a matching between the ride request event and the ride accepted event. That's done through the trip manager service. So it's listening for these ride requests, and it's listening for these ride accepted events. It acts on those to produce what we call a trip event, which goes back into the cloud and now goes back to the driver. It says, start driving to pick up Lindsay at his flat. And also emails or sends a notification to Lindsay to say, hey, your driver's coming, this is the car, and so on. So all of these things are happening basically simultaneously. infrastructure for this uses an open source framework called Apache Kafka. It works really well for Uber, but its limitation for scientific data is that all the data packets in Uber transmissions are really small amounts of data. Whereas if you're doing scientific data, you have large amounts of data, right, that you need to send back and forth. So in an NSF-funded project a few years ago, we, and again, I say we, it was a project that I was the PI on, but David Elbert, who I'll talk about a little bit later, was really the genius behind this, creating this thing that we call OpenMSI. What the acronym stands for is not important. I'm not sure I can remember anymore. But the key is that it allows scientific data streaming autonomously. And the way it does that is it takes the scientific data, which exists as these large bundles of data, breaks them down into the smaller transmissible bits that Apache Kafka relies or can handle. But the key is, because it's built on this very robust platform, it is itself very robust, very safe, and very reliable. We didn't just roll our own software, right? We built on top of something that already exists and is widely used, including by Uber, for example. Okay, so the basic idea is you have some data layer, and you can have data producers and data consumers interacting with that data layer. Now, it's not just a giant swamp of data organized into what we call topics. And so I can, as a data consumer, for example, I can subscribe to a topic that's relevant to my particular concerns. We can have multiple data producers and consumers simultaneously accessing this data layer. So again, in the context of the lab, different instruments can be writing to the data layer, different consumers can be reading from the data layer, all at the same time. Oh, one thing I should say about this is an open source project. It is device and OS agnostic. So there are versions of this that have been written and can be installed for Linux, for Windows, for Mac OS, and I'll give you examples of that as we go on. If I can get my screen to advance another slide. There we go. All right. So here's an example, and I think I've lost back. All right. So now I'm going to start pointing my hand. Except I did notice this fine stick. All right. So now we're going to use it. So I mentioned the photon Doppler velocimetry, right? So the data collection in that case is on an oscilloscope. And what that oscilloscope is recording is just the output of a photodiode. And so its data literally is intensity as a function of time. This oscilloscope runs an embedded version of Microsoft Windows. So we can load OpenMSI literally onto the oscilloscope. And there's a process there that now lives in the background. And anytime PDV data is collected, it goes into a folder. Our OpenMSI process is always watching that folder. And as soon as new data shows up, it takes those raw data and streams it up to cloud storage, or actually it's local on-site storage, but it could be cloud storage, into what we call our data layer. It's part of a topic, and the topic is raw PDV data. Now, in a different building, in a different location, there's another computer which is also now subscribed to that raw PDV data topic. And as soon as raw PDV data appear, they get streamed down, again, autonomously from the cloud to that computer. And that computer now does the processing. It takes the raw data, the voltage versus time, and converts it into that back surface velocity, which is the thing we actually care about. So then the reduced velocity data gets streamed again autonomously back up to this OpenMSI data layer. And now there's another computer someplace else which needs those data. So maybe this computer is using those data to figure out what the spall strength is of a material in order to update some machine learning model of the response of a material to different conditions. The key is that all of this is happening autonomously. There is no human involved anywhere in this other than installing the app at the very beginning. And so now if we're doing tests, at a rate of 1 every couple of seconds, our data streaming and our data analysis can keep up with that. But that's just a single instrument and a single topic, right? So here's our streaming layer. Every colored bar here represents one of these topics. All right, so maybe the raw PDV data is one of those topics. Maybe the velocity data is another topic. The key is that the Apache Kafka infrastructure is robust enough to have many topics running simultaneously. And so you can have many data producers, you can have many data consumers all accessing these different topics essentially at the same time. And that then, of course, turns out to be really important. Now, I may have given you the impression that streaming is basically just networking and moving data around. But I want to disabuse you of that, right? Streaming is not just networking. Streaming is a sequence of events. And it's a sequence of events in a topic, and a topic is actually a database. Right? So here's one topic. And the way to think about this is, here's our present moment in time. The flow of data or flow of events is from the future into the past. So here's where we're looking at events that are happening right now. Now our data stream is persistent in the sense that some recent past events are still there and we can still access them, but it's finite, right? We can't keep all the data in the topic forever. So after some period of time or after some amount of data that we specify, then the data disappear from that topic or the events disappear from that topic. The data still exists, right? They've been archived, they've been stored, we can go back and get them, but they're no longer part of this topic. The keys here, though, besides that finite persistence, is the idea that we can have multiple users of the same data, right? We don't have to send it just one place. Lots of different consumers can be accessing it, and all of this is being updated more or less continuously. Now, to give you the feeling for how this relates to a more conventional idea of a database, right? You may be used to thinking of databases more in the terms of batch processing. And by that, what I mean is you have a database of information which changes relatively slowly, but you may have many or very frequent queries of that database. So, the balances in bank accounts, for example, right, don't change that frequently, but there can be lots of accesses of that information. Hyperparameter tuning for an ML model would be another example of that kind of thing. String processing is sort of the opposite, right? Now the data is changing rapidly and is being used by logic elements that are themselves persistent. And a simple familiar example is a self-driving car, right? The logic behind the self-driving car doesn't change, right? That logic is all the same. What's changing is its state and its awareness of what's going on in the world. And that's the data which is going by very rapidly. So they're both sort of databases, but they're two different use cases for more or less for the data. And so where this really gets interesting then is we can create really, really complex sequences of operations and events. And this is illustrated again now for the context of this PDV data for the laser microflyer experiment. So here's our autonomous experiment. As I've already mentioned, the data from that autonomous experiment are autonomously streamed up to our streaming layer into a topic, which is the raw PDV data. There's an autonomous data processing stream, which is listening for that data and then writing the processed data to a different topic. Simultaneously, we have autonomous extraction of metadata and data curation that delivers these data into a human-readable form in the data portal, which a human can look at then and explore. And so besides just the velocity data, we get information on the noise and the uncertainty in the measurement and the statistics and these sorts of things. Simultaneously, then also, the data are then written to a database. So now that we have the metadata and we have the data, we can easily curate that and publish it into a repository, right? So this is something everybody talks about. My students hate it, right? Because it means they have to go through and they have to identify the relevant metadata and clean everything up, and then it gets posted to some repository where somebody can see it or not, right? But in our case now, this stuff is happening autonomously. Right? And so no human has to be involved at that point in the loop either. The other thing that happens is you can then, of course, have more complicated things that happen, right? So not just single events like the processing of the data or this relatively straightforward data curation and extraction, but in the case of something like the X-ray experiment, you can say, all right, I'm going to take the raw data, I'm going to do some basic processing, right? Find the beam center, do the calibration, do the azimuthal integration. Now I'm going to send that publish that to one of these topics. Now there's going to be another routine, which is going to do the phase identification, telling which phases are present and how much. Then maybe a machine learning algorithm sucks that down, right? All these sorts of things now can be automated and built out pretty robustly. Okay, so that's basically what I was going to talk about. I just put this slide up. I hope that you're interested in this OpenMSI idea. So this is software that was written at Johns Hopkins. But is being used at a variety of other places now. So besides a couple of labs at Johns Hopkins, in a couple of the electron microscope labs at Cornell, also at University of California, Santa Barbara. We've had some interest from a few European institutions. So I really recommend that you look it up either at this Read the Docs site, or this is an open source journal article that we published about it. It is pretty robust, and we are very interested in seeing it used more widely. So if you have problems, not even necessarily creating an entire lab, but just the idea that I need to be able to move data and operate it on an autonomous way, OpenMSI might be a solution. Okay, with that, I would just like to end with a couple of last slides, of course, to acknowledge the people that do the funding. One organization that naturally has an interest in materials in extreme environments is the United States Army. So most of the funding for this laboratory came from the Army. The development of OpenMSI and that data infrastructure was originally done under a grant from the National Science Foundation through their DIMREF program. And then some ongoing support comes from these two Hopkins centers, the Hopkins Extreme Materials Institute and the Center for Artificial Intelligence for Materials in Extreme Environments. In terms of acknowledging the people, of course, no lab like this gets built unless a lot of people are involved and working really hard. So I've not tried to list everybody that's involved in the lab. I'm only listing the folks here who are directly involved in the particular things that I talk about, particularly KT Ramesh, whom some of you may know has a longstanding interest in dynamic mechanical behavior of materials. So he's the genius behind the laser microflyer measurement. Tim Long and Michael Wall are postdocs in my group who helped develop the Maxima X-ray system. David Elbert is our data genius, so all the OpenMSI and this data streaming, everything that I know about that topic, David taught me. So he's the real expert there. Axel Krieger and Eric Walker are the primary driving folks behind the robotics and the controls. And then, of course, our staff engineers, Matt and Joseph, are instrumental in making things work in the laboratory on a day-to-day basis. One thing I'll mention, just in case it could be relevant for some of the people listening, Piyush, very talented postdoc working for KT. Piyush is currently looking for a faculty job of his own. So if you're interested in high rate behavior of materials, dynamic behavior of materials, and the intersection of that with ML and AI and autonomous laboratories, Piyush is really your guy. Haven't said anything about where the lab is. So we're sort of running out of space in the Johns Hopkins campus to build new buildings. So a few years ago, Hopkins bought this building, the Steve Silver building. It was a silver foundry where they made silver flatware. So the building itself is late 19th century, historic by American standards, not by European standards. But here are the workers, maybe the graduate students in the Steve Silver foundry, back again in the early part of the 20th century. So some things have changed. All right, that was the lab then. This is the lab now. So it looks a little bit cleaner anyhow. But some things have not changed. So back in the day, they like to take pictures of their team standing in front of their logo. Well, we like to take pictures of our team standing in front of our logo. So with that, I will thank you for your attention. I'd be happy to answer any questions.
Thank you very much. Exciting stuff. Over to you. Questions, comments? Yeah, please.
So I recently had to do a run of PDV analysis for spall experiments.
Oh, very good.
And I'm very jealous that you've got a computer to do it for you. Because I spent a lot of time squinting at spectrograms.
Yes.
Any tips for how to make it less hard on myself?
Less horrible for yourself. Well, I have to say that I am not the expert on that data analysis. However, if you want to talk to me after, I can point you to the journal article where the graduate student of KT Ramesh describes the algorithm they use for that automated process. And I'm sure there's lots of useful information in that.
So perhaps with autonomous vehicles in mind,
yeah,
I have in mind that things can go wrong and then you don't know who to blame.
Well, that's a feature, not a bug.
Yeah, well, okay. Why does that translate into this scenario? How can things go wrong? Could enemy agents be listening into your data transfer? Could somebody be developing a fraud?
Yeah.
Which would be easy to do as an individual.
Yep.
How does that all?
Yeah, so that's a really interesting question. So with regard to the data security, something that I did not say is that the OpenMSI framework, those data can't all be encrypted. Mm-hmm. And so they can be encrypted locally. They are encrypted in. We don't do it because nobody cares about our data. I didn't say that. It's recorded now. But seriously, so for example, the Army is interested in this. Yeah. And they, of course, naturally will encrypt their data. The question of data contamination, I think, is a good one, right? So there were some very interesting conversations we had recently. You know, if you're using publicly available open source data to train your ML model, there is the possibility that a hostile actor could decide to poison that data, right? And send your efforts awry. Some people that I've talked to say, I wouldn't worry about that because it sort of implies that if they know how to manipulate the data to send you in the wrong direction, that sort of implies that they a level of understanding of the problem, which is unlikely for anybody to actually have, right? So it is definitely possible to poison data in that way. I wasn't entirely reassured by that because, of course, you could be poisoning the data just by having gibberish, and there the point then is to cause people to expend resources in a fruitless search to find patterns where there are none. I would say, as an experimentalist, that's all the more reason to have a lab like this where you're generating your own data, and you do not have to worry about accessing other people's data in order to learn what you need to learn.
Yeah.
Follow-up question: how do you call it ontology? How do you structure your data? Maybe it's not my field here. We all have our ways that we look at data, and that's different fields. That might change every decade.
Yeah.
So now you have data recorded in a certain way. Come 10 years, and a few groundbreaking papers, let's say.
Right.
We look for different things.
Right.
We look for maybe this is more relevant, some defects relevant, whatever, humidity.
Right.
Your database currently is constructed in a closed way, is it? So how could I ever, because this goes back to data formats, right? I store,
right.
I format, I have a certain logic in mind.
Yes.
That logic might be undermined. That's what we do in science.
Right. Yes.
So how do we update? How do we keep data accessible? Also, when we change our complete models.
Yeah. So I don't have a perfect answer to that question, right? Because things like, you're exactly right. Things like data formats and things, those will change, and I guess at some point we have to start worrying about that. The way in which we're trying to do this now, and I did not talk about this in this talk, is trying to handle the metadata in a very robust way. So along with the actual data files, our JSON files, which are basically the metadata for the experiment. And as we have complete tracking of samples from the time that they are introduced to the system, from the time, through every measurement that happens to them up until the present moment. And so every time one of these events happens, information gets written to that JSON file. So for example, on the laser shock data, if that data is analyzed, when the data are collected, if the metadata is generated about the instrument that was used to collect them, which oscilloscope, what the settings on the oscilloscope were, and all that sort of thing. As the data get then processed, right, then there's metadata, which is this is the code that was used, this is the version of the code that was used, right? And I think that's about all that we can do at this point. I'm sorry?
You store the samples.
Well, we haven't made yes, we do store the samples. We haven't made such a large number of samples that we have to worry about like an archiving and warehousing problem. But yeah, ultimately we will. And then of course you have to worry about what's the longevity of those samples. But it's a very good point.
Please, yeah. Oh yeah, please do, yeah.
Indulging here.
Yeah, no, go indulge.
One generic question that we ask all, especially as a PI, right? Is that cost? So when I look at industry, if I scale and automate, there's a benefit if I will put it like a car.
Yeah.
I go to a product like a plane, and you got the point that it's not automated, it's manual labor.
Right.
So now I go to scientific lab. I have a problem maybe like yours where you shoot these things and it's always the same. I'm not undermining it.
Sure.
But maybe there are other areas where every so often everything goes out, completely new things come.
That's right.
Is it worth automating? Because that's basically the economics of science, right? Is it worth automating? Also at Cambridge University, I don't know how Johns Hopkins works. We get charged for that to the data. So actually doing all this, they charge us.
Yeah.
The university charges us. So
yeah.
It becomes actually crazy expensive.
Right.
And you ask yourself, what is it worth?
Right. Yeah.
So I don't know where you stand and what the viewpoints are on this.
So I have a couple of viewpoints on that. So the first is that the way I view this scientific research is that the development of the lab and the development of the capabilities that we need to address a particular problem and how we handle the data, that is a research problem in its own right. And so learning how to do those things and create this kind of facility raises its own research questions. You're exactly right in the sense of, if in the case of our primary funder, the United States Army, right, they have to make a choice about whether or not it is, it makes sense financially to invest in this. Right? So what I will say is that the techniques in this lab are fairly generic from the point of view of interrogating properties of microstructure materials, right? X-ray diffraction has been around for 110 years, 112 years. It's not going anywhere. People are going to use X-ray diffraction. I didn't mention this about the laser microflyer. I only talked about the spall measurement. But we can measure other things, right? So we can measure what's called the Hufnangel elastic limit, which is the onset of plastic behavior in a shock experiment. We can measure the equation of state, right? So there are lots of different things that we can measure. And the same thing is true with regard to the nanoindentation. It may very well be true that, we're going to use slightly different variations on those techniques for different problems in different contexts. But I think in the end, these techniques are going to be useful. But, there obviously are important limitations, and cost is an important part of that.
Yeah, so I do a lot of experiments, maybe I have 1 in 10, 1 in 20. I do something wrong.
Yeah.
Maybe something doesn't play out straight, maybe the suction cup gravel.
Right.
How do you handle on a data level identifying whether X interesting phenomena is something that is actually a property of the material versus a suction cup gravity?
Right. Yeah. So the details of that depend on the experiment, right? And I'll just give you one example. So I mentioned that we have this issue with the microflyer experiment. If this is my sample surface, we need to know, did the flyer actually impact, at 0 angle, or was it at a tilt, right? So that's part of the reason for doing the PDV from behind to measure the velocity on a multi-point basis, right? So if it's really a planar impact and we have a one-dimensional shockwave propagation, we should see basically the same thing at every point on the backside. So in certain cases, there are sort of built-in diagnostics to help you figure out if your experiment has gone wrong. In other cases, you can have kind of black swan type events, right? And so then the question becomes, well, is it an experimental fluke, right? Or have I investigated some phenomenon which is reliant on a distribution, let's say of grain size in my material, and I just happen to have tested a part of the sample where there's some microstructural variation, right? So part of the power of the data streaming idea is you can build in that kind of anomaly detection, and then you can decide, based on the anomaly that I see, is it worth my time to try to reproduce that experiment? Right, to go back, maybe I'll take the same sample and I'll look at a nearby region and see if it looks the same, right? We're still getting the lab going. We have not really tried to build that in, but that's in general, I think, how you would approach that sort of thing.
How far has OpenMSI stream come? Is this the first implementation of it, or is there what's the furthest field from what we're currently describing here?
The furthest field from what we're currently describing, I should say that I haven't been directly involved with OpenMSI in terms of its implementation in a year or so. So I don't exactly know what the latest is. The use cases that I'm familiar with, so one is nanoindentation at UCSB, but that's pretty closely related to what we're talking about here. The one which is probably farthest away that I'm aware of is at the electron microscope lab at Cornell, where they are now using OpenMSI to autonomously stream electron microscope images. But it's pretty agnostic to the kind of data, right? It doesn't, OpenMSI doesn't know that if your data is an image or a string of numbers of some other sort, basically any file, it will chunk and it will stream for you.
I was looking at that thing, but you can see this kind of automation fields that biology and chemistry as well. We're trying to automate concepts in very different ways.
Yeah. I haven't seen it go outside of material science, but that's mostly because the people that I and other people talk to are material scientists. I will say that David Elbert, who's that guy there, who's the data genius, he works really closely with people involved in the Materials Genome Initiative through the National Science Foundation. And so across NSF, there are people who are aware of this and the kinds of capabilities that this creates. And so I'm optimistic about its use.
Yeah, there's a lot of bespoke solutions coming up.
Yeah. So I would say that this is not a bespoke solution.
It's fine.
Because it does not care what the data are.
Yeah.
Right. It's it has a its fundamental understanding of the world is that data exist as files that are stored on instruments, right? But within that, right, once you have a folder that has data, OpenMSI doesn't care, and it will stream those data and send them, where you want. Now, where things get a little more tricky is every experiment, of course, has its own unique metadata, and things that are different from experiment to experiment in our lab in different places are, what is the form of that metadata, and how do you capture that metadata? So that can be a little bit more bespoke.
Maybe a query here. Or?
Wondering about, so like one of the biggest issues I've found with automation strategies. One of the biggest issues is ensuring interoperability between new automation and existing systems and workflows. I've got legacy workflows system. You guys have built quite a bespoke lab, I suppose. But I suppose how would you get around, like you say, getting around building automation around existing older systems? Is it worth just sort of gutsing it and starting again?
Well, I would say that we're fortunate in that we don't have any older systems yet, so that's good. So I guess there's sort of 2 or maybe 3 different ways to think about that, right? So one again is with relation to the data, right? And again, the data streaming architecture that I've described here, that really is agnostic about the form of the data and how they were produced, right? So it doesn't matter if it's an electron microscope, it doesn't matter if it's a diffractometer or a DSC or whatever. You can bring in a new one, you set up the client on that instrument, and it starts to work. Of course, some of the subsequent events, right, may depend, so if you're doing some sort of data processing, right, that data processing may then depend on, the form of data that were collected and therefore on the instrument. And so you would have to deal with that. Like I say, we try to do a good job of capturing the metadata so we always know for a given set of data what form they are. With regard to sort of flexibility in hardware, I'm not going to go back and show you those robots, but those are very general purpose robots, right? 6 degrees of freedom. And they only are doing actually 2 things for us. One is picking up samples off of the conveyor and putting them in the instrument and then going back. And then in the case of the laser shock, this assembly of those flyer stacks that I mentioned, the robots are doing that for us. But they're very general purpose instruments or devices. And if at some point we decided we could get better robots, then we could plug them in. One thing I didn't mention, there's like one corner of that loop where there is currently no instrument. And my idea there is we'd actually stand a robot there and allow users to roll their own test equipment up, right? Sort of like the idea of a CubeSat. You know what a CubeSat is? It's like a well-defined form factor for a satellite to go in a launching system to go into orbit. Well, my idea is if you can have something which is like a little optical table or a bunch of, frame built out of 80/20 hardware, right? You come in, as long as it occupies roughly a square meter of floor space and has reasonable utilities expectations. And if you've defined a way that I can hand a sample to you and then work on it, then you could have any experiment that you want, right? So it is designed, intended to be flexible in that way.
Okay. Go ahead, yes, the last one.
I was just thinking like nano indentation, like obviously that wears down over time.
Right.
And you've got to deal with, I assume you have to deal with that anyway, but
right.
Like that, but for this other equipment.
Yeah, no, it's a really good point. I was alarmed when just before I left last week that the engineer pointed out some metal dust which is accumulating at one end of our conveyor, which is a sign that there's some wear which is going on. So the real answer to that question, I think, is, and we have, don't get me wrong, we have not done this yet. But what we really need to do is we need to have, in addition to the data consumers, which are looking at the data that are coming from the different instruments for scientific purposes, we also can have data consumers which are essentially diagnostic, right? And so, as you probably know, as an indenter tip starts to wear down, right, you start to see that in the data, right? Maybe what you do is, in addition to just looking at sort of your unknown samples, or maybe that's a little bit hard to detect, you have standards that you go back to periodically, right? So part of the workflow could be, if the nano indenter is not doing anything else, we're going to stick in our standard, we're going to collect a bunch of indents, we're going to compare that to what we have previously, and now we're going to be able to sense if things are going awry. So again, we haven't done that yet, but it could be done. Yes?
How long do you spend to build such a good lab?
Well, let's see. So we, We started to move in the middle of 2023. So the lab is about 18 months old now or so. And where we are, I mean, I didn't sort of fill you into the entire like workings of the lab, but it's all of the individual stations are automated or close to it, with a couple of caveats. And the thing we're now working on is making sure that everything is actually integrated, right? So that we can actually move samples and have multiple things done in the order that we want at different stations. My guess is that certainly before the end of this calendar year, that problem will be tackled. So, in the end, it's going to have taken us between 2 and 2.5 years to build it out. With more resources, you could do it faster, right? If we had more engineers, but that's about how. Yep.
How much like downtime do you have? Like, what was the longest book that you had?
Oh, that's you shouldn't have asked that question.
Where is the contingency running?
So we've done things like stress tested with conveyance, right, and just moving samples around. And the longest we've run that has been basically a week at a time. The longest that we have like actually tried to do experiments at multiple different stations and moving things around, literally that's only been a few hours. But that's because we're still working on this integration problem. I sort of promised the Army, don't promise things to people with guns, but I promised the Army that by the midpoint of this year, we'll be able to demonstrate sustained operation of that.
Okay. Yep.
I suppose it's very automated. How long, how much time do people actually spend in the labs watching other things versus looking at something?
So that's a good question, and the where we are currently is that we are not comfortable with the robots doing things in the lab without a human there to at least be sitting in the control room looking at their phone, and if they hear a crash, right, be able to respond to that. I think because it's a university research facility, we are probably never going to get to the point where we're running for like days and days at a time without human intervention. I think probably where we are going to wind up is, where we'll have, for lack of a better term, a customer, right, that maybe has, let's say, 1,000 samples, right, with some variation in chemistry or microstructure, whatever that we want to look at. When we would run those in sort of a burst mode over the course of a few days, let's say. And then, of course, you would need some downtime, and maybe you need to replace the nano-indenture tip, or you need to replace a gear on the conveyance, or whatever. So humans are always going to be pretty heavily involved, but the amount of human involvement per test is going to be orders of magnitude less than what it is in a conventional lab.
We should probably wrap things up at that point. Let Todd escape. But thank you very much.
Thank you.
Okay.
And I will say, we are always looking for good graduate students and postdocs. So anyone who is interested in this would like to reach out to me, I'd be happy to talk.